Memory Trace Visualizer. Interactive visualization for memory reference traces. Scientific Computing and Imaging Institute, University of Utah. Motivation. Processor performance is steadily improving at such a rate that memory performance cannot keep up. Developers need a way to optimize the memory usage of programs to reduce the impact of this disparity. A reference trace is a record of all memory accesses made by a program. Each record indicates the access type and a target address. The trace is rich in information, but virtually impossible to understand by direct inspection. MTV visualizes the trace by displaying access patterns within user-defined regions of memory and their effects in the cache. The visualization shows reads and writes, cache hits and misses, corresponding source code lines, and the history of cache events. Visual elements. MTV provides several visual elements in order to display the contents of reference traces. Regions and cache. Regions are user-defined areas of interest in memory. Each region contains lines representing each data item. Regions are identified by a title and a unique color. Reads and writes are indicated by cyan and orange. Cache hits and misses caused by each access are indicated in the lower portion of the region. Each level of the cache is represented by an individual glyph. The upper color in each cache line indicates which region is currently occupying it. The lower part of each cache line indicates the hit-miss behavior resulting from the last access to that line. Blue means a hit to L1, purple means a hit to L2, while red means a cache miss. The color of the shell surrounding each level indicates temperature, or the proportion of access to that level resulting in hits. Lighter gray indicates a higher hit rate, and thus a warmer temperature. Here the L1 cache is relatively warm compared to L2. Animated lines relate individual accesses within a region to the cache lines with which they interact. Source code tracking. As MTV animates memory accesses in the regions and the cache, the corresponding lines of source code are highlighted. Here, the moving cursor illustrates the execution of a for loop. This provides developers a better understanding of the memory operations required for each line of source code. Examples. MTV can illustrate reasons for poor memory performance and guide developers to improved memory usage. Two simple examples are striding a two-dimensional array and matrix multiplication. Striding a 2D array. This example shows an array in two views, memory view and 2D matrix view. The reads move down each column of the matrix, resulting in a non-continuous memory access pattern. The striding pattern lacks locality of reference. Cache lines are flushed before they can be reused, resulting in a miss on every access. By reading along the rows instead of the columns, data is accessed while it's still in the cache. The result is a much higher hit rate and improved performance. Matrix multiplication. MTV can help developers map abstract concepts to corresponding memory operations. Matrix multiplication requires matrix Z to be accessed column by column. However, this results in poor memory performance. Using a block matrix multiplication algorithm eliminates poor striding patterns and results in higher hit rates. Conclusion. MTV exposes aspects of computer programs normally hidden from developers by compilers and hardware. By making reference traces accessible through visualization, MTV enables developers to create higher performance software. This work was supported in part by the U.S. Department of Energy through the Center for the Simulation of Accidental Fires and Explosions.